Hello class, hello students. Hey, Dr. Mann is here with another segment in thermodynamics. This video will be about Gibbs free energy. Previously, we've talked about enthalpy, bond breaking, bond making type energy, delta H, and we talked about entropy, the measure of the disorder, always favored by the universe. So it's always good to screw things up because the universe favors that. That's delta S. And basically, delta G is going to be the combination of delta H and delta S. The free energy is basically the sum of the contributing parts to a reaction. The parts of the reaction are bringing the atoms together, taking them apart, that's entropy, and making and breaking bonds, that's enthalpy. Enthalpy is measured in kilojoules, entropy in joules. So entropy tends to be a smaller number, but it's multiplied by a temperature, so that makes it big. So when we get down to it, we're going to have issues with unit conversions because delta H will be in kilojoules, delta S will be in joules, but delta G will be in either, usually kilojoules. But remember, free energy is just the sum of the enthalpy and the entropy. Entropy always works against us, so therefore entropy is sort of subtracted out. Because usually we're trying to put things together. Entropy doesn't really favor that. Entropy favors taking things apart. So if the free energy equation is made by Josiah Gibbs over 100 years ago up in Yale. And basically, it comes down to the free energy, delta G, is basically the sum of these two things, except it's negative because entropy usually works against you. Cool? Let's look at an example of this real fast. If you calculate the free energy change for that reaction, the Haber process, hydrogen and nitrogen becoming ammonia, you're given delta H and delta S. So all basically you plug and chug. The only issue when you plug and chug into this equation is the unit, J and Kj. Doesn't matter which way you go with it. I forgot to change that value. That is a mistake. It's like 32.4. Mess that up. If you do the math on these things, you have to be aware that this number is going to be in joules, this is in kilojoules. When I did it, I just switched 91,800 for kilojoules when I just add them into the calculator. For me, that's easier to say 91,800 than to, I don't know, somehow I don't like making that 0.198. But really, it's up to you. Just pay attention to your units. Okay, that's probably kilojoules per mole there. Sorry about that. Pay attention to the units. The free energy for reaction is a state function, gives free energy. So again, it's products minus reactants. And you're doing the same thing you did for enthalpy and for entropy. You have a knot there that refers to standard conditions, products minus reactants. I thought it would be good to just hash one out because I said this in the entropy video. Look, students often screw this up. There's a lot of data in there, man. There's a lot of data, so you need to pay attention and take your time with it. Punch in the calculator slowly. Some students like to write out more data than what I do. Just take your time with it because it's really common for students to make mistakes. Delta G is going to be the products, CO2, SO2, over here. And then you got 2SO2, that's why there's a 2 there. The products minus the reactants, CS2 and 3O2. So you go to an appendix in your textbook, go online, you find your Gibbs free energy values, and you just substitute. The units cancel, which is probably why I end up screwing up those units earlier. Moles cancel mole, mole cancel mole, mole cancels mole, but it's 0 anyway, so who cares? And you end up with kilojoules. And that's why sometimes your units are kilojoules for delta G, sometimes kilojoules per mole. That really just depends upon the source. And then by context, you need to apply the appropriate unit. Because delta G is negative here, negatives imply losses. So if the total Gibbs free energy of the system is going to be a loss, that's usually a favorable thing. Because if you're losing energy, then that means you have plenty of energy to begin with, and there's excess that's being released. The opposite of that, if you need to gain energy, is energy needs to be added into the system, and that slows things down or gums up the work, so to speak. So basically, when delta G is less than 0, when there's a loss, when it's negative, we're going to say that the reaction's spontaneous. Spontaneous here doesn't refer to how fast it happens, just that it will happen. Kinetics talks about how fast. This is thermodynamics. So when we say spontaneous, don't think it's fast, like being spontaneous yourself. It just refers to whether it will happen or not. So if reaction is occurring, then you can assume that the delta G is negative. If the reaction is not occurring, you can assume that the delta G is positive. Because sometimes on tests they ask you about hints of things, and one of the hints for the sign of delta G is that the reaction is actually occurring. That's all they say. This reaction occurs. And so you have to understand that delta G is negative. To summarize all this groovy little stuff, I have the table. I'd like to put it all down on one page if I can. Okay, maybe I can't. Often what you're given signs of delta H and delta S, and you're supposed to predict delta G. Alrighty? So if we're going to do that, whoops. Let's see. If delta H is positive and delta S is negative, I don't know why it's doing that to me. Okay? If we have positive and positive, we're spontaneous at high temperature. If the reason for that is, if you notice out here, I wrote out the equation. If H is positive, you're adding into it the entropy. The entropy is positive, but remember it's the opposite of the entropy. Okay, so in this equation right here, what you're looking at is a positive number minus a positive number. So you have two terms there. If the entropy term is bigger, then its sign will dominate. So delta G will be negative when entropy is big. And so that means high temperature. Okay, and the next one, here we see a negative delta H and a negative delta S. That means it's exothermic and a negative entropy. So over here, when we look at it, the only way delta G is going to be negative is if the delta H side of things dominates. That means we need a small temperature because that negative T delta S part, the negative T delta S, is going to change the sign of the entropy. So what I do is I look at this and I say, hey, I don't know if this will screw things up again. I have a negative delta H and a negative delta S. I just make that a positive. Okay. So when they're opposites, like they are here, the opposite hooks us up. If you have negative delta H and positive delta S, basically delta G is always going to be spontaneous, because if you look at the equation, you got a negative delta G and negative, because delta H is negative, minus a positive, so delta S will always contribute in negatively, so to speak, because that opposite sign. Same gig down here. If delta H is positive and delta S is negative, then minus makes the negative a positive. So whenever you have this situation here where you have endothermic and negative delta S, the reaction is never going to be spontaneous. The only way you can determine spontaneity is by comparing enthalpy and entropy, because they both combine to say whether something's spontaneous. And you sort of need to just work that out, the two sides of that Gibbs free energy equation. Because just to summarize, Gibbs free energy is the sum of delta H and delta S of the enthalpy and the entropy. Hope this explains a little bit for you. Like it. I'll talk to you later. Take care.